Okay, so we've just talked about what significance means, and really significance, statistical significance, just means that according to some criteria, the results are unlikely to be due to chance. But we've seen that usually p less than 0.05 means it's just a less than 1 in 20 chance, which aren't particularly long, and you are going to get significant effects where there aren't any, with a probability as low as high as that, 1 in 20. So there's a kind of difficult balancing act that's going on here, which I'll introduce to you in a second. What we want to do is for our test to detect an effect which is there, right? And we want it also to not erroneously detect effects aren't there. Okay, this is getting a bit confusing. Hopefully it'll become clear in a minute. So this is the world of type 1 and type 2 errors. And again, another statistical horror story here. We've talked about significance, which is a terrible word. Type 1 and 2 errors, completely meaningless to most people and very easy to get them confused. Some people have proposed that there's also a type 3 error, which is getting mixed up between what a type 1 error is and a type 2 error. So let's imagine this is in terms of smoke detectors. We have a smoke detector, and that either goes off or it doesn't go off here, and then down here we have whether there's a fire, if there's a fire or no fire. So there are 4 possibilities here. So let's say there's a fire and the smoke detector goes off, right? Yes, that's a correct decision. That's great. The smoke detector has done the right thing. It's gone off to warn you that there's a fire, to get out of the house, to not die. On the other hand, there's no fire and the smoke detector doesn't go off, which hopefully is most of the time in your house. Again, that's a correct decision. It's not alerting you to something that isn't there, which is what you want. However, there are 2 failings here, 2 times when it goes wrong. Because the smoke detector can go off, yes, when there's no fire, no. This is a false alarm, or a false positive, or a type 1 error. So this is where the smoke detector goes off but there's no fire. So this can happen quite often, as I'm sure you're aware, with smoke detectors. However, there's another failing here, which is where there is a fire but the smoke detector fails to go off. That's a false negative, or a type 2 error. And obviously that's horrible. You know, having a smoke alarm go off when there's no fire is irritating, but having a smoke alarm not go off when there is a fire here is potentially fatal. So smoke detectors tend to err on the side of detecting things that aren't there, rather than not detecting things rather than failing to detect things that are there, because the consequences are massively worse in one than the other. So when people design smoke detectors, they tend to make them a little bit kind of overly sensitive, just to prevent these false negatives from happening. Trying to prevent false negatives from happening necessarily makes false positives more likely. So we can adjust the sensitivity of our smoke detector. We can turn it up, which reduces the likelihood of false negative, or we can turn the sensitivity down, which reduces the likelihood of false alarms, but increases the likelihood of false negatives. So you can see with smoke detectors, that makes perfect sense. Statistical tests are exactly the same thing. We can have the test return significant, yes, and there's an effect, yes. Correct decision. We've successfully found something which is there. On the other hand, our test returns no significance and there's no real effect, and again that's a correct decision. The test has failed to detect an effect which isn't there. Again, that's the same as our smoke alarm not going off when there's no fire. That's good. The 2 problems here, but exactly the same thing, is that we test for significance and we find a significant result, but there's no effect. That's a type 1 error, or a false alarm. We say, oh, there's a difference between these 2 groups, but in reality there isn't. On the other hand, the other problem is a type 2 error, where we fail to return significance, but there is an effect. And again, same kind of thing, there's a balancing act here. We can make our tests more or less sensitive. Increasing the sensitivity of the test makes it less likely to return a false negative. In other words, a type 2 error, but it makes it more likely that we have false alarms. If we reduce the sensitivity to the test, we decrease the likelihood of making false alarms, but we increase the likelihood of failing to detect test effects that are actually there. Now, generally, statistical tests tend to, unlike smoke alarms, we tend to want to avoid false alarms at the expense of saying, well, maybe we'll have a few more false negatives, because we don't really want to be continually finding effects that don't really exist. So we tend to err on the side of caution. But we can adjust this. We can simply adjust this by making the p-value more or less stringent. The smaller you make that p-value, so if you make that p-value, that's 1 in 20, 0.05, 0.01 is 1 in 100, 0.001 is 1 in 1,000. So if you make it very small, 1 in 1,000, you're very unlikely to find something which isn't there, false alarm, but you become increasingly likely to fail to find things that are there, and that can't be good either. So there is a balancing act going on here with these kind of statistical tests. So significant testing tells us whether the results are likely to be due to chance or not. Smaller the p-value, the more likely the result is due to chance, but we can also change this. We can increase or decrease the test sensitivity. Increasing the sensitivity is at the expense of making it more likely that we find false alarms and so on. The other measure of interestingness is known about but not as widely talked about. Here's a question. There are two lotteries which cost £1 a head. Lottery A has a 1 in 20 chance of winning some cash. Lottery B has a 1 in 100 chance of winning some other cash. So that's P equals 0.05 and P equals 0.01 in terms of probabilities. Which would you rather play, A or B? Trouble with that is what you don't know is how much you win. So for example, if Lottery A you have pretty good odds of winning, but you only win a small amount, but Lottery B you might have not very good chance of winning, but you win a considerably large amount more. So if you want to work out your expected outcome here, the potential gain of Lottery A is 1 in 20, so that's 0.05. We multiply that by the cost, then we get an outcome of 0.5, a net return of 0.5. Potential gain of Lottery B, that means that the net benefit is twice as big as in Lottery A, because although you've got less chance of winning, you've got less chance of winning considerably more than in the first case. So we don't just want to know how likely something is, as found by statistical tests, such as t-tests and so on. We'd like also to know how big the prize is, how big the effect is. For example, we might find that a drug trial finds that on several thousand people finds that a particular drug increases well-being in depressed patients by a significant amount. That might think, well, let's go down that route and spend the money. But hang on, how big is this effect? How big is this improvement in well-being? It might be statistically significant, but is it a big effect? Is it big enough to warrant the extra expenditure for the new drug? It could be only a tiny increase, but nonetheless, because you've got lots of participants, a big sample, you can say it's not a difference that's due to chance, but the question is it big enough to warrant the extra expenditure? So if you think of a test as a lottery, the p-value is your chance of winning, the effect size is how much you win. It's a very simple terms. So here's a piece of research here which shows that men are significantly taller than women. We know this. But how big is this difference? How big is this difference? In fact, it is a fairly big difference. We can see here that the average height of a man is about 71 inches, whereas the height of the average woman, and it is normally distributed data, is about 64 inches. So there's a relatively big difference of about 5 inches, 6 inches between the average man and the average woman. So that's quite a big effect. So the sex difference in height, it says at the bottom here, is a thing called 1.4. What does 1.4 mean? Well, one of the measures of effect size is simply a thing called Cohen's d, which says how much bigger is one mean than the other, again in units of standard deviations. We saw this with z-tests. We're not looking at the difference between each score and the mean, as we did with looking at the z-scores earlier on. What we're simply saying here is if we look at the overlap between the two distributions, how big is the overlap? And we can see in this graph here, is it a relatively small overlap here, where the difference between the two distributions is a standard deviation of 0.05? Is it a standard deviation of 1 difference, standard deviation of 2 difference, standard deviation of 3 difference? This is one way of saying how big the difference is. So the sex difference in height between men and women is around 1.4 standard deviations. Right, so it's a fairly big difference. So Cohen says, in terms of interpreting these numbers, that anything bigger than 0.8 is strong. Around 0.07, sorry, about 0.7 is moderate to strong. Between 0.45 and 0.65 is moderate. Around 0.4 is weak to moderate, and less than 0.2 is weak. So the sex differences in human height between males and females is very, very strong, stronger than pretty much any effect in psychology. We consider ourselves doing one of the really big effect sizes in psychology tend to be about D of 0.7. So D of 1.4 is a very, very big effect size. So this is big, obviously, compared to many other effects, but if we were to compare us to other animals, such as gorillas, chimps, bonobos, baboons, elephant seals, the sex difference in height in those kind of animals is much, much bigger than it is in humans. So we've again got to be careful about how to interpret the word big. Statistically, it might be a big effect, but it's useful to have some kind of baseline to compare it with. Correlations, when you do a correlation, it actually comes with its own effect size. They measure the relationship between two variables. So we're not looking at differences here, we're looking at whether shoe size is correlated with height, or whether intelligence is correlated with how much broccoli you eat, where we're dealing with two continuous variables, not discrete variables like male versus female, or condition 1 versus condition 2. We can tell whether the relationship is positive, so the more broccoli you eat, the more intelligent you become, or negative, the more lead you consume, the less intelligent you become, or no relationship at all. If your data meet parametric assumptions, remember, is at least interval level, or it could be ratio as well, but at least interval level, normal distribution, lack of outliers, then you can use a Pearson correlation. If they don't meet parametric assumptions, you can use a Spearman correlation, both of these in SPSS. This is just so-called scatter plots showing positive, negative relationships and no correlation whatsoever. Now, what correlations do provide you with, they provide you with a significance level. Is there a significant correlation? But remember, all that means is this relationship between these two variables, is it likely to be due to chance? If it looks like it's less than 1 in 20 due to chance, then we return significance. But it also gives us the correlation coefficient. The correlation coefficient tells us how big the effect is, how strong the relationship is between these two variables. Now, correlation coefficient is somewhere between -1 and +1. You very rarely get -1 and +1 because that would be a perfect relationship. It doesn't usually happen. But the closer that the correlation coefficient is, usually denoted by R, if it's a Pearson correlation, or rho, the Greek letter rho for Spearman correlation, the closer that is to ± 1, the stronger the effect. There's a thing called variance. Variance is simply the extent to which the proportion of variance is the amount that one particular variable accounts for in the other. So if we have a correlation coefficient of 1, then if we multiply that by itself and multiply that by 100, then we turn it into a percent variance. So a correlation coefficient of 0.1, well, that's 0.1 times 1 is 0.01, multiplied by 100 gives us 1, rather depressingly. So a correlation coefficient of 0.1 means that there's a 1%, one of the variables accounts for 1% of the variation in the other. Very, very small. It means that the variable is accounting for, is failing to account for 99% of the variance. And similarly, we've got correlation of 0.5, 5 times 5 is 0.25, 0.25 times 100 is only 25% of the variance, and so on. So this is a measure of how strong the effect is. So this is a useful thing to bear in mind. It's not just about whether it's significant, it's about whether how big the effect is, how strong one variable accounts for the other. Very much, as we saw, like Cohen's D.